Good morning. My name is Charles Forsberg. Today I would like to discuss baseload nuclear systems for variable electricity and hydrogen with heat storage. It's part of a series of activities at MIT on how to develop a system approach to a low carbon system. The outline is that I will cover energy challenges of a low carbon world, then describe systems for nuclear power and heat and hydrogen storage. That will be followed by conclusions. But the important thesis of the entire talk is as follows. It is the system's design that controls energy costs, not the specific details of any particular technology. Let's first take a look at energy challenges of a low carbon world. The first challenge is the low carbon world has very different economics than today's fossil systems. If we look at the left at a fossil system, we see a combined cycle natural gas plant. It has low capital cost, high operating cost. Those characteristics enable economic operation at part load. If we look at a nuclear system or a solar system or a wind system, these systems have high capital cost and low operating cost. It is uneconomic to operate these at part load. If you operate these at half load, you approximately double energy costs. So the question is how to economically match production with demand. Let us start with a second observation. That is, there is a mismatch between electricity production and demand, and we're going to use the California case. In the figure, we see a dark black line, which is the smooth daily California electricity load. The dotted line shows the smooth daily renewable outputs for wind and solar, where we've adjusted those wind and solar outputs to produce the total amount of electricity needed in California over a year. And what we find is there's a mismatch. In the summer, there's a surplus. In the winter, there is a shortage. So there's a seasonal problem that we must address. Now, if one had an all nuclear system, the match between production and demand would be better, but still there would be a serious mismatch between production and demand on a seasonal basis. Now let us take a look at what the customer needs. Most energy consumed in the United States is consumed as heat. Electricity is only 17.5% of consumer energy demand. This figure shows on the left various types of energy sources: nuclear, geothermal, fossil heat, that is natural gas and coal, biomass, and fossil heat in the terms of oil. On the right, we find what the customer requires: residential, commercial, industrial, and transportation. In the middle, we see the electricity sector where we convert various energy inputs into electricity. What is most striking about this is that almost all the energy used by society is used in the form of heat. For example, if we look at the industrial sector, the electrical input in gold is insignificant or very small relative to the heat input. Indeed, the electrical output of the entire United States is only equal to about half the heat input into the industrial sector. Now, in a low carbon world, nuclear is the low cost energy source. And we show here various technologies showing the levelized cost of electricity and the levelized cost of heat. And we show this for PV, for wind, natural gas, and nuclear. Now, the levelized cost of electricity for most electrical technologies and the levelized cost of heat for most applications is the same. And the reason, of course, is quite straightforward. In most applications, particularly where you need higher temperatures, you use resistance heating, and 1 unit of electricity equals 1 unit of heat. However, in the nuclear case, it takes 3 units of heat to produce 1 unit of electricity. And as a consequence, nuclear reactors produce cheap heat, but more expensive electricity. The other feature of our electrical system is that roughly half the cost of electricity is the cost of delivering that electricity. So if electricity is used for heat, it implies high heating costs. In short, electrically generating technologies, wind and solar, produce cheaper electricity. Heat generating technologies such as nuclear produce lower cost heat. With that, let us turn to the system design for nuclear power with heat and hydrogen storage. Remember what our goal is: minimize the total cost of energy. We show here a low carbon systems diagram that includes heat and hydrogen storage. I'm going to go through this figure component by component in the next 10 slides. In the middle of the slide, in the red boxes, is the heat generating sector. We have the nuclear reactor, we have heat storage, and we have the option of a combustion heater as a secondary heat generation source. Going upwards from the heat sector in red, we go to the electrical sector, where we have energy conversion systems, heat to electricity, such as a steam turbine, converting electricity back to heat, and of course, wind and solar that produce electricity, yielding in all cases electricity to the electric market. Taking a look at the heat systems sector in the middle and going downwards, we go to the hydrogen economy. We're going downwards, we have heat markets, that is the industrial heat market, and the heat market that goes into high temperature electrolysis that produces electricity. So with this division of a sector going from heat to electricity and a second sector going from heat to hydrogen, let us look at the individual sector components. Our first component is the system designed for nuclear power with heat storage. Here we show the heat electrical sector and the capability to buy and sell electricity. On the right, we show the price of electricity over one day in California in the spring. As one notes here, in the middle of the day, there are low, very low prices that are near zero. This is because of the large installment of solar voltaic in California. At times of low solar and wind demand, the morning and the evening, we have very high prices, particularly right after sunset, which also corresponds to peak electricity demand. So that is the market. How do we address the market? We start with our nuclear reactor. The nuclear reactor operates at base load. At normal times when electricity is needed, steam from the nuclear reactor goes to the main turbine generator on the left in the middle set of boxes to produce electricity that goes to the electric market. At times of low electrical demand, low electrical prices, the nuclear reactor in the lower left box sends its heat to heat storage. Now, if there's times of high electrical prices, nuclear reactor heat and heat from heat storage goes to a turbine generator set that produces electricity whose output to the electrical market may be 2 or 3 times the base load price of electricity, base load production of electricity. At times of very low electric prices, near zero, our system buys electricity, and the electricity is converted to heat that goes into heat storage. At the same time, the nuclear reactor's heat goes to heat storage. What this system does is it adds electricity when the grid needs it, it subtracts electricity when the grid does not, and in effect, it will set a minimum price of electricity that helps both the nuclear sector and the solar and wind sectors. Now, it turns out that heat storage is relatively cheap, and there are many, many options. The DOE heat storage goal is $15 a kilowatt hour, but new technologies may reduce this to $2 to $4 a kilowatt hour. The electric battery storage goal is $150 a kilowatt hour, and you double that if you include electronics. And the difference is the raw material costs. On the table at the right, we show different storage technologies that could be used with light water reactors or more advanced sodium, salt, and helium-cooled reactors. And we take a look at what is behind these individual storage technologies. We have geothermal, which of course is storing heat underground, crushed rock, oil, cast iron, nitrate salt, and chloride salt. what is noteworthy about all of these storage options is their costs are very low relative to the components that would be used in any electrical storage system. Now today, batteries are 3 to 4 times more expensive per kilowatt hour than heat storage. In the future, that difference may be larger. Today, nitrate salt storage is used at the gigawatt hour scale in concentrated solar nuclear power plants. There are 3 generations. Generation 1, which is deployed today, is nitrate salt in large tanks. This particular technology would be applicable to advanced light water reactors. At lower temperatures, the storage material would be a heat transfer oil. The second generation heat storage systems use crushed rock in oil or salt in the tanks. The reason why, of course, is crushed rock is less expensive than oil. Third generation systems, one looks at using crushed rock as a heat storage component, and the oil or salt is sprayed on the crushed rock and used to move heat from the reactor to heat storage to the turbo generator, but is not part of the storage system. It's only a heat transfer fluid that is used to move heat from point A to point B. The noteworthy feature of Generation 3 heat storage is it may drive capital costs down by a factor of 10 to perhaps $2 to $3 per kilowatt hour of storage. Extraordinarily cheap storage relative to any other systems. Let us now look at nuclear power with hydrogen production and storage. There are 2 components that we must remember about hydrogen. First, there's potentially a very large hydrogen market. The US market is currently 10 million tons per year. There are several future hydrogen markets that are almost assured in a low carbon economy. The first one is replacing fossil fuels as chemical reducing agents to produce iron. In most cases, there are no other options. You need a chemical reducing agent. The second is for high temperature furnaces where one needs very high temperatures. And of course, hydrogen burning can provide those very high temperatures. There are also 2 potential mega markets, much less certain because they have other competitors, that is the transportation and the replacement of natural gas. The second feature about hydrogen is that bulk storage is extremely cheap, as has been demonstrated for the last 40 years in various parts of the United States. Hydrogen can be stored underground in a variety of different geologies. We show here a picture of hydrogen storage in salt caverns in Texas. And you can see the surface facility on the left and a schematic of what those underground caverns look like at the right. Now, depending upon which scenario you believe in or which hydrogen future you think might happen, potentially 15 to 30% of all energy consumption could be in the form of hydrogen for a wide variety of applications. Now, there's one catch. All hydrogen production methods are capital intensive. We have electrolysis, which is electricity plus water. We have high temperature electrolysis, which is likely the low cost option. This is steam electrolysis, so part of the energy input is low cost hydrogen, low cost heat, I mean. More importantly, higher energy to hydrogen efficiency than other processes. In other words, the total amount of energy needed to get a kilogram of hydrogen is less for a variety of technical reasons. There are thermochemical processes, which are heat plus hydrogen, and of course, steam methane reforming of natural gas, the current production technology, plus additional carbon dioxide sequestration. The key feature of all of these technologies, however, is you have to operate them at high capacity factors because the capital costs of these plants are very high. You can't afford a hydrogen future with hydrogen plants operating at low capacity factors. Now let us take a look at high temperature electrolysis using heat and hydrogen. Here we show the top part of the system is the system we described earlier. The bottom part of the system is the hydrogen system. And of course, we have high temperature electrolysis, which needs electricity from the electricity market or nuclear reactors, and it needs heat that can come from the nuclear reactor or the heat storage system. The hydrogen can go either into storage or directly to the hydrogen markets. So again, on the middle of the diagram, we have the heat technology. Going upwards, we have the electricity technology. Going downwards, we have the hydrogen technology. Now, When electricity prices are high, reactor heat and stored heat from heat storage is used to produce electricity. There is no hydrogen production. When medium prices, we produce hydrogen and electricity, some mixture of the two. When we have low electricity prices, we buy electricity from the grid for hydrogen production, and all of the reactor heat goes to the high temperature electrolysis unit or the heat storage system. In effect, this becomes a massive sink for excess electricity on the grid. What's the implication of this? We show here a nuclear hydrogen electricity system based on the fact that first, hydrogen is storable, so we can meet the demands of the customer no matter what our production facility is. We have a plant that produces two products, hydrogen and electricity, and the nuclear plant becomes an electric peaking plant. 80% of the time it produces hydrogen, as shown on the right. 20% of the time it produces electricity. That electricity can be used at times of peak power demand, including seasonal demand. Where does this leave us? It leaves us with several conclusions. First, this system allows the high capital cost components, the nuclear plant, the wind and solar plants, and the hydrogen plants, to all run at very high capacity factors to minimize cost. Second, the economics is made possible by two factors: low cost heat storage, coupled to the nuclear reactor, and low cost hydrogen. This is the storage in the system that matches production with demand. With that, I will end this discussion. Look forward to any questions you may have. You can contact me at the Massachusetts Institute of Technology. My email is cforsber@mit.edu. Thank you.